Hello and welcome to ADS Python tutorials. This is tutorial 5 in which we will talk about using Python based synthesis IPs in ADS. This is going to be a very interesting video because this explains how you can bring your own custom synthesis IPs and integrate it into ADS and make you best use of your time and expertise available and innovate much faster. And now you are no longer limited by the tool's capability as long as you have your own design methodology or a synthesis IP to design the kind of circuit you would like to do. So here I am going to take a couple of examples to illustrate two different things. And I'm taking filter as an example because this is the easily understood topic by most of the RF microwave engineers. So I'll take a couple of case studies. One is on the lumped low-pass filter design, and then we can take a look at a microstrip low-pass filter design. And after we have those computation, we will proceed with simulation and result plotting for each of those case studies. And again, the script I'm going to use in this video can be downloaded from the link provided in the description box of this video. So in the first script, we will start with a given set of design specification, and then we will walk through the entire process till we have this complete simulation result, and then we will compare from where we started and what we have obtained with our synthesis code. Similarly, for second example, I will again start with a given set of specification to do high frequency low pass filter design, and then we will compute all the related parameters and then design or create a schematic with microstrip line defining the microstrip substrate and then perform simulation. So again, it's going to be pretty interesting video, so I hope you will stay till the end and grab everything which I'm going to talk about and then make best use of it at your own site. So as always, keep exploring more videos in this playlist to deepen your understanding. Alright, let's get started and talk about the first example. Here I'm taking a simple example of LC filter as I just talked about, and let me copy paste the first section into my Python console. And here you can see I'm importing some Python modules and then related ADS module that we need. And then I have the filter design specification. As you can tell from specification, is a Chebyshev filter with a specific passband ripple, cutoff frequency, stop band frequency, and the required attenuation at the stop band frequency. And then I'm defining certain workspace variables like name of workspace, library name, cell name that we need to create. Now after that, we have our filter synthesis code, and in this function we will pass all those specification as an input argument, and then I'm using a textbook based formulas to compute inductor and capacitor values for our filter circuit to meet the given specification. So let's execute this piece and note the desired characteristics of the filter. So our code computed that we need a 7th order filter, and if so, we will get rejection of almost 53 dB at our stop band frequency, which in this case is 1.5 gigahertz. And then these are inductor and capacitor values. Now once you know the inductor and capacitor values, and that is available in a list or array as we call it in normal programming language, now it's very easy to go ahead and create a schematic, place a variable block and assign these values to those variables. I have already discussed this in one of the previous videos, and if you haven't watched previous videos, I would recommend go ahead and watch those earlier videos so that you get a full clarity on how to proceed from this point on. Now assuming you have seen the previous videos, I will go ahead and use and execute these functions to create workspace and the design schematic with the required components, and then I will also add a variable, and in this variable I will keep assigning the values we have computed for our inductors and capacitors to create the filter design, and also place the S parameter controller with the desired characteristics so that we can later simulate it in the desired frequency range. So at this point, let's go ahead and execute our code. We can see the schematic got created, and let's open that schematic. And here we can see the 7th order filter design with the related S parameter block and the variable with the values our code computed for the filter network. So it's pretty straightforward at this point. Now here, if you want, you can go back to Python and continue to create netlist and plot the results. But before we do that, if you want, we can also execute the simulation here and then plot the results to see what kind of performance we have obtained and how close it is to our Python code. So here you can see the S21 and S11 plot, and let's insert a marker at 1.5 gigahertz frequency, and here you can see the rejection offered is minus 53 dB as predicted by our code. So this tells you the code I have provided does a pretty good job. It can create the inductor capacitor based low pass filter very effectively, virtually in no time. So this way you can have your own IPs and you can be very productive, not depending on whether the tool has that synthesis capability or not. As long as you know a little bit of Python coding and you have those calculation equations, you can be up and running in no time. Now one thing to note here, although from practical aspect, you can see the inductor and capacitors used here are ideal in nature. That means they have a very high Q factor. In real practical application, you will always use a vendor component that has a finite Q. Now if that is needed, you can do two things. One, either in your Python script you can account for that Q factor if you know the formulation available, or while creating the ADS schematic design, instead of placing these inductor and capacitors in an ideal nature, you can always place components like inductor with Q factor, capacitor with Q factor. It's just a very small modification to your existing code, which you can download from the link provided. And here you can see if you use these components, you can specify their Q factor, the frequency at which Q is mentioned, and so on. And this data is very easily obtainable from a vendor datasheet, or you can directly use vendor library such as Murata, TDK, Coilcraft, etc. So those kind of vendor library can be used as well. Alright, so this was our first example showing you that we have indeed done a pretty good job in designing. But since we were already doing everything in Python, and I stopped in between to show you the data display and the result which we obtained. But let's finish the task by creating the netlist, processing the results, and then plotting it. And again, all these things I have already discussed in the previous videos, so I'm not talking about that in greater detail in this video, but you're always welcome to watch earlier videos. So here you can see similar, in a way same S21 and S11 response which we just saw in the ADS data display. Alright, so that completes our first example demonstration. So let me close this workspace and then let's go to our second example, where we will talk about microstrip based low pass filter design. Again, the half of the story is exactly the same like we already discussed. So here let me copy paste this section here, and again you can see I'm importing certain Python modules and certain ADS module, and then I have a design specification for a microstrip low pass filter. You can see little higher frequency since we are going to do high frequency design. So cutoff frequency of around 2 gigahertz, the stop band frequency of 3.5 gigahertz. The only change compared to the previous script, so let me open that here. So in the earlier script, we were providing the required attenuation as one of the inputs so that the code computes the number of order required in order to meet that specification. In this case, just for the sake of variety, I'm using a different method of synthesizing filter where order of the filter is one of the input arguments, and then we create filter constraint based on the number of order. because sometime in microstrip you have a size constraint and so on. So you can do some early calculation and then restrict your design only for a specific number of sections, since you already know the wavelength you are dealing with and the size limitation you have. But again, you can feel free to use the previous function here as well. Now, considering those, and since we are going to do microstrip design, I also have few dielectric parameters such as dielectric constant, loss tangent, height of the dielectric, and so on, because ultimately we would transform all the inductor and capacitors into distributed form, and that will be done based on the dielectric which you plan to use to create your PCB. And also, since we are dealing with printed transmission lines, there is a limit of minimum width or the recommended maximum width which you will have from the fab house. So we also need to put some constraint on what is the highest impedance you would like to use and what is the lowest impedance that would you like to use. The highest impedance will affect the inductance, and that is what we will use for the inductive section of the filter, and the low impedance we will use for the capacitive section. So these two will put a constraint on what is the maximum inductance you can obtain, what is the minimum maximum capacitance you can obtain, and based on that the length of the section will be determined. So you don't want to put any arbitrary number which cannot be fabricated in real life. So that we will take care by putting these constraints here. Also, since we are dealing with a dielectric which has a finite amount of loss tangent, this will also give you a certain Q factor, and your filter performance will be affected by the quality of the dielectric. So our code takes care of all these practical aspects in mind, and then once we transform or design a filter, we will work through these constraints and get whatever best possible. And again, for input and output side of the filter, we need certain feed length so that you can mount a SMA connector and so on and so forth. So all these practical aspects you can use in your code, so that the code generated circuit is a very good start point for your circuit implementation. All right. Okay, so again, these are the workspace variables, and here is the filter design function, which initially gives us the inductance and capacitance required for that filter. So let's go ahead and execute that function and then introduce certain print statement to print out the results which we have obtained. So in this case, you can see is the 7th order filter as we wanted, and then these are the inductance and capacitance values for the desired frequency and the design characteristics, and estimated attenuation at 3.5 gigahertz is around -48 dB. But this attenuation is based on idealistic inductor and capacitance. Now, based on the dielectric qualities, as we just discussed, this rejection may or may not be achievable, and that's what we are going to see in the next section here. Alright, so once we have discrete inductance and capacitance value, our job is to transform it to the microstrip equivalent, and that's what we are going to do next. So let me copy paste this section here. So you can see I have a function here which does microstrip calculation for the desired impedance, and that is what we will use to compute the width of the inductive section and the width of the capacitive section based on the dielectric constant, height of the dielectric, and the impedance which we have targeted for those sections. And after that, we will do the length calculation to achieve the inductance from the given highest impedance and the lowest impedance possible. So let's execute this, then we can print the result out. And here you can see we have the inductive section line lengths, we have the width of the inductive line, we have capacitive section widths, and the capacitive section line lengths, so both of them, and then 50 ohm width for the input and output at a given dielectric we are going to use. Now once we have all these inputs, we know the topology we would like to implement, we have the parameter values. Now the job is pretty simple, which is again to create the workspace library and your circuit design, and then simply simulate it. So let me go ahead and execute this function, which basically does that. And here is the synthesized response of the filter, where you can see a decent filter characteristics, but around 3.5 gigahertz. If you notice, we are getting rejection of around 35 dB, whereas in idealistic inductor and capacitor case, it was predicting around 48 dB rejection. That's observation number 1. The observation number 2 is, you can see the cutoff frequency was supposed to be 2 gigahertz, but this seems to be closer to 2.2 or 2.25 gigahertz. So there is something wrong happening. So let's discuss what is that we are missing. So let's open this schematic here. And now you can see these cascaded inductive and capacitive lines, and with the right set of variables. And from our code, we created 2 variables, one for the inductive section, one for the capacitive section. And we also placed the microstrip substrate on the schematic. But here you can notice the width of the capacitive line is around 5.5 millimeter, whereas the width of the inductor is 0.13. So that's a huge impedance ratio. And you can see here, I have not connected the microstrip step to calculate the discontinuity effect when your high impedance line gets connected to the low impedance line. So in order to get a better clarity, let's go ahead and create a layout. And this will also show you the schematic we have created from our code is almost ready. And now you can, even if you want, you can proceed for electromagnetic simulation. So here you can see these line junctions. We have not accounted for this impedance mismatch in our schematic design. Hence the response which you are seeing in Python is not exactly the same which you hoped for. But if you modified the provided code and include the microstrip step in between those lines, then this will show you the right behavior. So that work, I leave it to you. But in order to prove that, let me go ahead, place a couple of pins at input and output, and let me create a stack up property based on whatever we have defined in the schematic size. So I can go ahead and import the definition from our schematic design. So if you are aware of ADS, I think you are already aware of this process. So now we have 3.66 dielectric constant, 20 mil substrate with a conductor of 0.5 ounce thickness. So this is the stack up I'm going to use for my EM simulation. So I can go ahead and switch on RF Pro, select that cell LPF1 dielectric, click OK. And now we have our circuit in RF Pro. And now if you want, you can perform momentum simulation, you can perform FEM simulation and so on. So let me quickly add those pins to create 2 ports, as you can see at input and output. In the options, I will go ahead and simulate it till 5.5 gigahertz. Now from DC to 5.5. Simulator, I will pick momentum microwave with 30 cells per wavelength. And let's run a quick simulation. It shouldn't take too much of time to run this simulation since it's not a huge structure and I have a pretty decent laptop where I'm running it. So as you can see, the frequency sweep is running, and once it is completed, I can go ahead and plot the S21 and S11 result in the S parameter graph plotter. So here if I plot S21, now you can notice the cutoff frequency is actually at 2 gigahertz because electromagnetic simulation is already accounting for that mismatch loss. So there is no confusion here. And then let's put a quick marker at 3.5 gigahertz. And now you can see the rejection is around 37 dB. And the idealistic inductor capacitor gave you around 48 dB. So again, if you had a dielectric with better properties like better loss tangent or something, you could have hoped for a little higher rejection at that frequency. Again, but this is not bad. Starting point, if needed, you can optimize your design and you can obtain the required attenuation or change with filter order a little bit. So we can also plot S11, which also looks pretty decent, better than minus 15 dB of return loss till you pass band frequency and so on. But you can see you have a very good start point now to fine-tune the design the way you want and then be more productive instead of doing repetitive things all the time. So that's all for this video. I hope the content presented is going to be useful for your work and you would be able to do a lot more by bringing your own IP into the Python console and not getting limited by the tool's capability and functionality and the kind of synthesis programs which is available. So go ahead, feel free to innovate, and thanks for watching this video till the end. Look forward to see you in the next video.